Hello and welcome to the lesson for 12.5, everybody. This lesson deals with tree diagrams, and so we're going to learn about these vocabulary words and phrases here, and let's get right into it. So make sure you're using those extra examples in your book to check some extra things out. If this stuff doesn't make sense to you, check them out. But a tree. So a tree, this is without its leaves, so it makes it a little easier to see. A tree diagram is very much like this, where things are going to be branching off of one particular node, you might say, and then they keep branching off, We're going to be using tree diagrams in a mathematical sense to help us understand probability a little bit. So let's get started with some vocabulary first. So the counting principle, this is going to be extremely important for the remainder of this chapter. The counting principle, knowing what this says. And I think it's fairly intuitive, fairly obvious, but this is what it says. And this is a much less technical sounding version than what the book has. So I'm just saying thing, quote unquote, a thing. So if one thing can happen, the book will word it a little differently than this. But if one thing can happen in M ways, I'm just trying to condense it a bit, make it more in layman's terms, you might say. So if one thing can happen in M ways, and a second thing can happen in N ways, then the things in that order can happen in, so I'm saying one thing happens and another thing happens right after that. What's the chance, or how many different ways, I should say, can that happen? That can happen in M times N ways. You multiply them together. So the number of choices you have for the first thing is M, the number of choices you have for the second thing is N. Together they can happen in M times N ways. The sample space what is sample space? It is the list of all possible outcomes in an experiment. And then one more vocabulary term, something we need to know. Sample point. What is a sample point? And then we'll get into some examples after that. So a sample point is each individual outcome, or each point, in other words, each individual outcome in the sample space. You've got your sample space. It has all the possible events, or all the possible outcomes, and then each individual outcome is a sample point. So in the sample space, there we go. And let's check out some examples now. So we're going to see some branching off. It's not going to be quite this elaborate. We're not going to have this many branches, but kind of just depends on the problem what you have going on. So two marbles. This is the situation here. Two marbles are to be selected without replacement. We'll talk more about what that phrase means later on in this problem. Without replacement, but that's pretty important. Underline that for me. Two marbles are to be selected without replacement from a bag with one red one green and one blue marble. And we're going to split this problem into three separate parts. So part A, we're going to get started here with part A. And before we write this out, let's draw a situation of that. So off to the side on this one, I want you to draw kind of a bag, any old bag. Mine I'll have look like that, so my bag doesn't have handles on it. But you don't have to use different color for this, but I'm going to just to make it easier to see. But I want you to label one of the marbles with a G for green, one of them with an R for red, and the other one with a B for blue. So we'll say we have a bag, 3 marbles in it, like that. And part A, where you're going to draw a tree diagram to determine the sample space. And remember from our definitions, the sample space is just a list of all possible outcomes. So determine the sample space. So what's a tree diagram look like, Mr. Wagner? Here we go, tree diagram. You've probably done some stuff like this in the past. Don't write this down. This is just a little tidbit of information or a little explanation of where we're going with this. You've probably done stuff like this. From prime factorization, you split up 15 into 3 times 5. You split up 18 into, and you can do like 2 times 9 or 3 times 6, but you can keep splitting these things up. This is an example of a tree diagram. This isn't what we're going to do here though, but that's the similar idea. It's the same sort of thing, same idea, same concept, but this is with probability now. So we're going to start here. We're going to say we're starting at some point like right here. And so from there, from where we start, we can go in 3 different directions. We can either pick a green, a red, or a blue. And so let's draw that here and here. You're going to want some decent space because from each one of these points, it's going to split off even further. So we're going to need plenty of space here to do all this. So this one, you could have, I'm just going to go in order, red, green, blue. So we'll go red, R for red, G for green, B for blue. That's your first option. This is your first pick. So let's put that down here. I'm going to use parentheses down here because this will go along with this. I'll kind of show you another way to think of it in terms of the counting principle. How many choices do we have there? We have 3 different choices. So 3 choices here. This isn't necessarily to do part A, but it's going to help us understand things better probability-wise. From here, you can split in 2 different directions because it's without replacement. So that just means you don't replace it. You don't put it back in the bag. So if you picked the red one first, that's no longer an option. The green and blue would be options. I'm not going to erase that thought. I just want to think of that. So if you did pick the red one, it's gone. You have green and blue to pick from. So you'd have a G here and you'd have a B there. So let's put that down right here and right here. If you pick the green one, that one's gone now. You'd have red or blue to choose from. So over here we should put an R and a B. And if you pick the blue one, you'd have a green and a red to choose from. So I would put R and a G. Alright, so there is my second pick. That's my second pick right there. How many choices do you have for the second pick? Well, you picked one out, you didn't put it back, so you had 2 for the second pick. So the counting principle will tell us 3 times 2, you should have 6 different possibilities, 6 points in your sample space, and that is what we have. So 6 points. This is our sample space, and let's draw our sample space out or write it out over here. So sample space, this is what a sample space would look like. It's the list of all possible outcomes in an experiment. So we have to list all the possibilities out. One possibility is R and then G, which would be red and then green. Then we have R and then B, so red and then blue. Green and red, GR, green and blue, GB, B and R, BR, and B and G, BG. So this is our sample space. There we go. And this is our tree diagram. So we did both of those things, and then this was just a little extra explanation, but make sure you have that written down underneath it like that. So this will line up here. 3 times 2 gives you 6 points in your sample space. Okay, I'm going to need to insert a new page for this. Just a second. There we go. So let's continue this. We got part B. Part B is to find the probability, and I'm just going to put it like this. So probability of 1 blue marble selected. So probability of 1 blue marble. rather than write out the question. I think we can understand it from that. So what's the chance or the probability of one blue marble being selected? If we go to here, don't circle these things, this is just for you to look at right now, but what are the different ways that one blue could be selected? You could have this, you could have this, you could have this, and you could have this. There's 4 different ways to get one blue out of 6 total possibilities. And so if we think of probability as what you want over the total, that makes it really easy. What do you want over the total of ways that things can happen? You want one blue over the total number of ways. And so there are 4 that give you one blue out of 6. That's the same thing as 2 out of 3. So that is the chance there. And then here I want you to write that this, let's use a different color for this. So right here, where did this come from? The 4 came from the 4 possibilities, the 4 outcomes in the sample space that had a blue to go with it. So RB, GB, and then those things switched around. So RB, GB, and then BR, and BG. Those all had one blue marble. So write that down off to the side, and then let's answer part C. We're going to say this instead. What's the probability of green followed by a red? So the chance of picking a green marble and then picking a red marble after that. How many different ways can that happen? Where do you have green and then a red? Right here, and that's it. There's no other way you can get green then red. Yes, there is a way you could get these 2. You could get red then green, but I'm saying specifically green followed by red. And so there's only one way to do that out of 6 possibilities. And so this would be, again, what you want over the total. This is what you want, and then over the total, I think we have that idea down, I hope. So I'm just going to put the numbers down right away. So there is one way to get green followed by red over 6, and there's no way to reduce that, so that is your final answer. In color though, pointing to the 1, let's put that the only way was GR. Right, and now let's move on to a second example. Sorry if you're hungry right now. We're going to talk about food in this one. And here's the problem. Here is the situation. Suppose you have a choice of chicken, which we're going to refer to as just a capital C as we continue this problem. Chicken or beef. Beef will have a capital B. And sorry, 4 meats. Let's put that down. So you're gonna, sorry vegetarians out there, this one we're gonna have some meat here. I suppose I could have put tofu in there, but I'm leaving that out. I'm gonna try to keep our number of choices down a little bit so we don't have a crazy amount of stuff to write down. We're gonna get the idea here. You may have a lot more branches in your tree diagrams with later problems, but for right now, I'm trying to keep it more simplistic as we just are learning about this stuff. Zucchini, Z, squash, S, or P, potatoes, P. That would be, yeah, not good. Okay, P, potatoes, as a side dish. And lemonade, L, or milk, M, as a beverage. So sorry, no water, no carrots. This is your choice. This is what you got. This is all we cooked up. Part A, tree diagram time. Alright, so let's draw a tree diagram to determine the sample space once again. Sample space, there we go. This one just because I can, and I think it'll make it a little bit less expansive, or it'll fit better onto our paper this way. I'm going to put this one kind of going vertically instead of horizontally like it was on the other one. So that's fine if you want to do your tree diagrams breaking off this way instead of breaking off that way. So this time I'm going to start here, and I'm going to go with my choices for meat, splitting off here and here first. Spread these out fairly far apart because we're going to have a lot of different things branching off of each one there. So your choices for meat, you had chicken or you had beef. So I'm going to put a C here for chicken, a B here for beef. So this is for your meat choice. And then from there you've got a choice of a side dish. So from each one of these it's going to be branching off 3 directions because there's 3 different side dishes. So you could have zucchini, you could have squash, and you could have potatoes. Here you could have same thing, zucchini, squash, potatoes. And then from each one of those you can branch off twice again from there. So we have lemonade and milk. So we're going to have an L and an M coming off of each one of these. L and M, L and M, L and M, L and M, and L and M. Wow, okay. So how many choices do you have? So you started here, you had a first choice to make, and then a second choice to make, and then a third choice to make. So your meat choices, we take this and think about it this way. Let's write this off to the side. I'll put this in parentheses. It's not a necessary part of the problems like these later on, but it's going to help us see what's going on here. So for meat we had 2 choices. For the side dish we also had, we had 3 choices, and for the beverage we had 2 choices. So if I take all these, this times this times this, if I multiply that together here, 2 times 3, that's 6. 6 times 2 is 12 choices, or 12 points in our sample space. Alright, so this is kind of in a weird set of parentheses here, really big parentheses. But the sample space, what's it look like? So this one's aligned a little differently than this was back here. That's fine. As long as you list them all, as long as you don't forget any of them, that's okay to list them this way too. It doesn't really matter to me. So you have C, Z, and L. That's chicken, zucchini, lemonade. You have, so I'm going here, I'm looking at the end one here and going back up. So that one included L, Z, and C. This one includes M, Z, and C. So this one was chicken, zucchini, and milk, and keep doing the same thing. So this one's chicken, squash, lemonade. Oops. Chicken, squash, lemonade. And then we have chicken, squash, milk, chicken, potatoes, lemonade, chicken, potatoes, milk. And then we have our beef choices. We've got, it's all going to be the same here except the C will be replaced by the B. So I'll just write all that down. In your sample space here, we did the counting principle here to figure out how much it was. We do the tree diagram, same thing. We get the same number of choices, points in our sample space. So BZM, BSL, BSM, BPL, and beats per minutes, BPM, or beef, potatoes, milk, if you prefer that. Yeah. All right, that's our sample space. That is our final answer for part A there, along with the tree diagram. So part B, we're going to do another one like that. Part B, like before, so the probability of what's the chance getting milk and squash in a meal. We are going to, let's write this off to the side. For B and C, we're going to assume equally likely outcomes. This is important, very important to make this note, because it might not actually be equally likely that somebody would like squash as compared to potatoes. You probably you take a survey of everybody in America, and there's probably going to be more people that would choose potatoes over squash. But we're going to assume that each choice is equally likely. So 1/3, 1/3, 1/3. It's basically, think of it like being randomly drawn from a hat or something like that. Their choices are randomly selected. So we're going to assume these equally likely outcomes, and we'll figure out from there the probability that milk and squash is in the meal. What is the chance of that happening? And so what you want is milk and squash, and what goes on the bottom is still the total, so it's still a probability question. Milk and squash over the total. So how many of these have milk and squash? If we go back to that, let's look at our sample space and let's circle each one. You don't have to circle it, don't circle it yourself, but let's just look here and circle the ones that do have both of those things. So I'm looking for milk and squash, an S and an M. There's an S and an M, and here's an S and an M. None of the other ones have both S and M, so it looks like there's 2 out of 12 total possibilities. So I'll erase that there, and that gives me my answer. So we have 2 out of 12, and that equals reduced to 1 out of 6 in a different color to remind us of where this number came from later when we look at this. Write this down, that was CSM and it was BSM. That's why there's 2 things. Those 2 were the only 2 that included both squash and milk. And so another way to think of this, let's do this in a different color too. You could have thought of it like this too, that the probability of picking milk, since there's 2 choices for a beverage, this is 1/2. So that's the same as the probability of picking milk, and in this case would refer to times the probability of picking squash, which is equal to 1/2. And the probability of picking squash, there were 3 choices for the side dish, which is 1/3. So if you multiply 1/2 and 1/3 together, this is another way to think about getting the probability of milk and squash. So you can do it this way, using the counting principle of probabilities multiplying together, or you can do things this way too. Right here I'm wanting you to use the sample space that we wrote out, but this is another way to think about it. So I want you to include that with your notes too, so that you know that for later. We did that in a different color though, because it's kind of like something that I'm telling you in addition to what we're learning about in this lesson. We're going to learn more about this kind of stuff later as we move along. Alright, what's the probability now of no chicken? Probability of not picking chicken. And if we look at our sample space, which ones don't have chicken? Well, it's this whole bottom part. So anything with beef doesn't have the chicken. And so there are 6 things that have no chicken out of 12 total possibilities. In your different color, please write down the 6 things in the sample space that did not have chicken. So it's all this stuff, BZL, BZM, and so on. So BZL, BZM, and then beef squash lemonade, beef squash milk, beef potatoes lemonade, beef potatoes and milk. So that's where the 6 comes from. And then this can be reduced to 1/2. That's our final answer. And then get that different color back out again, because I want to talk about this alternate way to think of it, but later on we'll be talking more about this kind of stuff. So this would be the same thing as the probability of no chicken would be the same thing as 1 minus the probability of picking chicken. 1 being 100% in terms of percentages. The probability of picking chicken is 1/2, and so this would be the same as 1 minus 1/2, which equals 1/2. And so that's another way to think of this problem as well. And one more thing I'll have you write down here. This sort of idea could come in handy later on. So this 1 minus idea, we'll put that on the last, or my last page here. So write this down. You may find this handy in some situations. We're going to use this idea a lot more as we continue with part 2 of this chapter for us. You may find this handy in some situations. And then I'll put a box. This is pretty useful, pretty important. Put a box around that. So the probability of an event happening at least once equals 1 minus the probability that an event does not happen. So we didn't really use that in this lesson, but it is introduced in this lesson, so I'm going to bring it up here, and we will definitely be using this a lot more later on. You may see this idea useful in your classwork. Hope that helped, and let me know in class if you had any questions. Thanks, guys.